Okay, hi. So the last lecture we talked about the shear in the ZX component generated by VX, which is 16,000. Now we have another shear force. So now the shear force will be acting in this direction now. And it's inducing a shear force of 2,500 Newton. So what we see over here is we can sketch our shear flow. So you're going to do, so it's going to do this direction, coming into here, get into here, and then it's going to go out. So this is a wide flange section. So again, this is our element A, and the axis is intersecting now, is the x-axis. Alright. So what you realize now, the shear flow due to Vy and the shear flow due to Vx is in opposite direction. Okay, so Vx is going towards the left, Vy is going towards the right at element A. So still the same thing, we still find the shear, right? Z in the X component and XZ. So this will be equal to, so this is known as our Vy is in the Y direction. Okay, so that's our Vy. Again, this will be Ixx, first moment of area about Qx, and then you have the thickness. Okay, so we know that Vy will be equal to 2,500 Newton. Ixx, we also knew what's our Ixx. So it's 40.8 times 10 to the power minus 6. And then the thickness over here is the thickness of the flange, which is the same like before, it's 11.8 times 10 to the power minus 3. Okay, so next is Qx. So where we want to calculate Qx? Okay, so this is the point of interest up to here. Okay, so we're going to find Q about the x-axis, which is equal to A y bar. So the y bar is the distance from here to here. So that is our y bar. So area is equal to width, so it's 0.075 multiplied by the thickness, 11.8 times 10 to the power minus 3, and then we have to get y bar. So D, the value we got for D is 166. So let's check. So D, is equal to 0.205, not 166, 0.205 minus by 11.8 divided by 2. Okay, so this will be equal to 0.205 divided by 2 minus 11.8 power minus 3 divided by 2 times by 11.8 power minus 3 times by 0.075. So you get 85.491 times 10 to the power minus 6 meter cube. So from here you can immediately calculate our shear ZX, shear XZ, So this will be 25 times 10 to the power 3. The first moment of area is 85.491 times 10 to the power minus 6. Divide by 40.8 times 10 to the power minus 6. And then thickness is equal to 11.8 times 10 to the power minus 3. So what we have over here is 4.439 times 10 to the power 6 Pascal, and it's going towards the right because it's flowing the shear flow over here, going towards the right. Okay. So now you can assemble everything, okay, into your element now. So this is element A. So I'm going to draw our respective transformation, X, Y, and Z. And we know that stress Z is equal to 28. We have calculated stress Z. So we 28.852. megapascal. And then the shear, we don't know which direction we are using yet. Okay, so the shear, so I'm going to declare positive, okay, is going that direction. Okay, we're going to declare that. So the shear XZ, shear ZX is equal to, so it's coming down, so 6.00465 times 10 to the power 6, and this is in this direction, and this is due to, this one is due to what? Due to, we should calculate, this is due to Vx, and then minus 4.439 times 10 to the power 6, and it's coming down direct. It's minus because it's in the opposite, and this is due to Vy. So the outcome of this, so 6.0465439 is equal 1.6075 times 10 to the power 6 Pascal. So it's going in this direction. Okay, sorry, there's a shear arrow, not normal stress. So the shear is in this direction. So 1.608 times 10 to the power 6 Pascal. Okay, right. So we are going to do 3D Mohs circle. I'm going to go real slow now because I like to explain Mohs circle. So this is point X, this is your point Z, and this is your point Y corresponding on Mohs circle. Okay, so we know that structure is under tension, and then we're going to draw 3D Mohs circle now. Okay, so 3D Mohs circle and 2D Mohs circle, they are very similar in a lot of ways. Okay, so we're going to draw our x-axis, so this is our 0, maybe I'll go from -5, 0, 5, 10, 15, 20, 25, 30, and then you go up to 35. So this is our normal stress, and the scale we have used for the normal stress and shear stress has to be the same. Then you will get a circle. If not, you'll get an oval. Okay. So this is 5, 10, 15, 20. So over here, shear is in a clockwise element rotation, a clockwise direction. Okay, so over here is minus 5, 10, 15, minus 20. And then this, the element rotation is clockwise, which I'll elaborate what do I mean. So we are looking at, so what we have is stress X and stress Y is equal to 0. Stress Z is equal to positive 25 or 28.852, and shear ZX is equal to shear XZ is equal to shear ZX, and it's in a negative shear configuration. So what do I mean by negative shear? So if this is our element in 2D, okay, so if this is our I'm going to call this my X and Z plane, positive shear, the arrow will behave this way. So positive shear, and then negative shear will be in the opposite direction. So this is what we call by negative shear. Okay, so that's why the arrow is going that way, which is this configuration over here. That's why it's negative. And then finally, we also know that shear XY is equal to shear YX is equal to 0. And we are also aware that shear YZ is equal to shear ZY, and it's also equal to 0. Okay. So the first point we're going to identify is stress Z is tensile by 28. So just approximately, this is our stress Z line, 25, 26, somewhere around here. So this is our stress Z line. And then the shear we get is 1.608. So 1.608. Now, in shear, you have to draw either at the top, at the bottom. The positive and negative for the shear does not mean anything. It depends on the rotation of the elements. Okay, so which I will elaborate. So it can be either at the top or at the bottom. So now, whether it's at the top and bottom, it depends on the rotation element. So we know that it's negative shear. So we are also aware that this is your point X and this is your point Z. So let's focus on Z first. Okay. So we know that stress X and stress Y is on the 0 line. Okay. So stress X, you look at this arrow over here, the element is going to rotate in stress X in a what? In a clockwise direction. So clockwise direction means stress X, this point over here, this is our point X, right? And then if you look at the Z, which is on the stress Z line, right? You look at this arrow over here, you fix the center point. Okay, so this center point, I'm going to draw it fixed. So when it rotate in a what? The element due to the pink shear stress that I've just drawn, okay, will rotate in a clockwise direction. So clockwise is below. Clockwise, is anti-clockwise. Okay, so this is your stress Y. All right. So for now, you can, if you have a compass, you can immediately draw this now. Okay, draw a circle, and then you calculate your normal stress and maximum stress and your principal stress. So we can achieve this through calculation also. Okay, so let's calculate what is our so center of the circle. No need to memorize any formula. Will correspond to our stress average. Will be equal to stress X or stress Z plus by stress X divided by 2. So we know that this is 29.853, 0 divided by 2. So 29.853 divided by 2 is 14.9265 times 10 to the power 6 Pascal. Okay. Then we can find the radius of the circle. Which is equal to our tau max. So this is a square root of 14.926. So what we are trying to find here, so we found where our stress average is. So if I go, so it's 14.925, so it's close to 15. So this is our stress average line. This is 14, so we'll be somewhere around here. Okay. So 14.926, in fact, I'm going to move it slightly towards the left. So as you can see, this is our stress average line. So to find the radius, so this is our radius. We know this height, we know this distance from here to here. So all we need to do now is 14.9265 squared plus by the shear, which is equal to 1.608. You don't need to put the plus or minus because when you're squared, the minus just disappear. It's 15.012 or 15.013 times 10 to the power 6 Pascal. Okay, so we found our tau max already, and then we find our stress 1, our principal stresses. So our principal stresses, stress 1, 2 is equal to stress average 14.9265 plus or minus 15.013. Okay, so you have two possible solutions. So the first one is 14.9265 minus 15.013 is 0.0 minus 0.0865 megapascal. And the other one is equal to 29.9395 megapascal. So we have identified the principal stresses acting on the element and the maximum shear stress. Okay, so I'm going to sketch the circle out. Okay, so you will pass slightly to 0. And you go slightly beyond 30. And then you go 15. And you go 15. Okay. Okay, so this is our mold circle, and if you were to ask me where is point Y, so point Y is in fact inside here. Okay, right, so this over here is your point Y. Okay, so now we have identified the principal stresses and the maximum shear stress on element A. Thank you.